Time feels like a steady, invisible river, always moving us forward. But is it really the same for everyone? We build our lives around the idea that time is constant, measured by clocks, shared by all. Yet what if time could speed up or slow down? What if your time and mine could flow differently? Over a century ago, a brilliant mind dared to question this, transforming our understanding of reality. So, let's begin. Can time actually slow down? The answer is yes. Imagine identical twins, Anna and Ben, living synchronized lives until Anna becomes an astronaut. She travels near the speed of light while Ben stays on Earth. For Ben, 40 years pass. For Anna, only 5. When Anna returns, Ben is 60, but Anna is just 25. Their shared time has split. Anna's journey through space slowed her journey through time. This isn't science fiction, it's a real effect predicted by physics. The twins' story reveals a profound truth: time can flow differently for different people. How can two twins age so differently? The answer lies in Einstein's theory of special relativity. Einstein asked, "What if the speed of light is always the same, no matter how fast you move?" To make this possible, time itself must be flexible. The faster you move through space, the slower you move through time. This insight unlocked the mystery of the twins and changed our view of the universe forever. Einstein reimagined the universe not as separate space and time, but as a single fabric, space-time. Everything moves through this fabric, tracing a path through both space and time. When you move faster through space, you move slower through time. This is why Anna aged less than Ben. Our motion through space and time are linked, two parts of a whole. This is the foundation of relativity. Einstein's breakthrough solved a puzzle. The speed of light is always constant, no matter how you move. If you're on a train or standing still, you measure light's speed as the same. To keep this true, space and time must adjust, stretching or shrinking as needed. There's no absolute time or space, only the speed of light is absolute. This radical idea overturned centuries of physics. It's why time can slow down for a fast-moving astronaut. Picture Anna on a speeding train, measuring a light pulse bouncing to a mirror and back. For Anna, the light travels straight up and down. For Ben, watching from the platform, the light travels a longer diagonal path. Both must measure the same speed for light. Since Ben sees the light travel farther, he must also see it take more time. This means time runs slower for Anna on the train. Time itself bends to keep the speed of light constant. A light clock is a fundamental concept in physics. 1 tick is the time it takes for light to make a round trip. For someone traveling with the clock, the ticks are short. But for an observer watching it move, the light travels a longer path. Since the speed of light is constant, the time for 1 tick is longer. The moving clock is ticking more slowly, a real effect called time dilation. If time slows down, everything inside the moving train slows down with it. The person inside wouldn't feel anything different. To keep light speed constant, time itself must become flexible. It is a fundamental property of space-time. The faster an object moves, the slower it moves through time. Now that we understand the connection between space and time, let's push this idea further. If moving faster through space means you move slower through time, what happens as you get faster and faster? This brings us back to that ultimate cosmic speed limit, the speed of light itself. Nothing with mass can ever reach it. As an object accelerates and gets closer to the speed of light, time dilation becomes more and more extreme. To actually reach the speed of light would require an infinite amount of energy. Let's imagine our astronaut Anna in her spaceship. As her speed climbs, Ben would notice that Anna's clock is ticking slower than his. This isn't science fiction, it is a direct prediction of Einstein's theory. The closer you get to that ultimate speed limit, the more time stretches. To gain speed through space, you must sacrifice your speed through time. Let's return to our story of the twins, Anna and Ben, and put some real numbers to their fantastic journey. Imagine Anna travels to Proxima Centauri, about 4 light-years away. If Anna's spaceship travels at 80% the speed of light, the journey would be a grand undertaking. From Ben's perspective on Earth, the total distance is 8 light-years, taking 10 years. After 5 years, the ship reaches Proxima Centauri, turns around, and begins its 5-year journey home. But for Anna, time is passing much more slowly. At 80% of the speed of light, her time is slowed. The journey that Ben measures as taking 10 years will, for Anna, take only 6 years. When Anna returns, she will have aged by 6 years, while Ben will have aged by 10. This is the essence of the twin paradox. Let's step inside the spaceship and see the universe from Anna's point of view. However, if Anna were to look out of her window back at Earth, she would see time on Earth running fast. She would watch 10 years of Earth's history unfold in just 6 years of her own time. Instead, something else must change. Just as time dilates, space contracts. The 4 light-year distance to the star system appears shorter to her. Space-time has warped around her to ensure that the speed of light remains the same for everyone. Time dilation and length contraction are 2 sides of the same coin. Let's return to Ben's experience on Earth. For him, time unfolds at a familiar pace. He is the stationary observer who simply has to wait. 10 years is a long time. Fashions change, governments rise and fall, and technology marches onward. Ben is our anchor to familiar reality, the baseline against which Anna's journey is measured. This contrast pits our earthbound understanding of time against the consequences of space travel. When reunion arrives, Ben is 10 years older, while Anna has experienced only 6. Time itself has passed differently for each of them. It is not a universal metronome, but a personal quantity affected by motion through space. We've explored how speed affects time, but what about gravity? Einstein realized gravity's effects are indistinguishable from acceleration. Gravity isn't a force, but mass warping spacetime. Massive objects bend spacetime, and other objects follow these curves. If gravity is curved spacetime, it must affect time. Stronger gravity slows time. This is gravitational time dilation. Time runs slower at sea level than on a mountain. Time is relative to both motion and gravity. To understand warped spacetime, imagine a trampoline representing flat spacetime. A bowling ball creates a dimple, warping the space. A marble rolled across now curves, even orbiting like a planet. The sun, like the bowling ball, warps spacetime. Earth, like the marble, follows this curve, which we call its orbit. Planets aren't pulled. They roll along spacetime's contours. Gravity also warps time. Time runs slower closer to massive objects. This is a fundamental feature of our universe. The effect of gravitational time dilation isn't just something that happens near massive stars and planets. It actually happens right here on Earth, all the time. The effect is incredibly small, but with modern atomic clocks, we can measure it precisely. So, let's imagine another story, this time with 2 climbers. Let's call them Chloe and David. They both have incredibly accurate, perfectly synchronized atomic clocks. Chloe decides to stay at a base camp at sea level, while David sets off to climb to the summit of a very high mountain, like Mount Everest. He will spend a few weeks at the top before returning. David's climb takes him further away from the center of the Earth. This means he's moving to a location where Earth's gravity is just a bit weaker. According to Einstein's theory of general relativity, this means time for him should run just a tiny bit faster than it does for Chloe down at sea level. For every moment that passes, David's clock will tick ever so slightly faster than Chloe's. While he's on the mountain, breathing the thin air and enjoying the view, his personal river of time is flowing at a different rate than hers. The difference is minuscule, a matter of nanoseconds, but it is real. During his time on the mountain, neither Chloe nor David would notice anything unusual. Their own experience of time would feel perfectly normal. A minute would feel like a minute to both of them. They would go about their days, eating, sleeping, and working, without any strange sensations. The effect is far too small to be perceived by our human senses. It's only when they are reunited and can compare their incredibly precise clocks that the difference would become apparent. This is not a thought experiment. It's a real experiment that has been performed many times. When David descends from the mountain and meets Chloe back at sea level, they place their clocks side by side. What they would find is that David's clock is now slightly ahead of Chloe's. He has aged just a few nanoseconds more than she has. While he was higher up, his time genuinely ran faster. This tiny discrepancy is a direct confirmation of Einstein's theory. It proves that your position in a gravitational field determines the speed at which you experience time. The closer you are to a massive object, the slower your clock ticks. Gravity's influence on time is woven into the fabric of our everyday world. If gravity from a mountain can create a measurable difference in the flow of time, what happens when gravity becomes incredibly strong? What is the most extreme case we can imagine? The answer lies in one of the most mysterious and fascinating objects in the universe: a black hole. A black hole is formed when a massive star collapses under its own gravity, squeezing an immense amount of mass into an impossibly small space. The gravity it produces is so powerful that it warps spacetime to an absolute extreme. The depression in our trampoline analogy becomes an infinitely deep pit. Imagine a brave or perhaps foolish astronaut who decides to travel towards a black hole. As their spaceship gets closer, an observer watching from a safe distance would see the effects of gravitational time dilation become more and more extreme. Time on the spaceship would appear to slow down dramatically. The astronauts' movements would become sluggish. Their ship's lights would shift towards the red end of the spectrum, and their clock would tick at a crawl compared to the observer's clock. The closer the ship gets to the edge of the black hole, the more pronounced this effect becomes. The edge of a black hole is a point of no return called the event horizon. This is the ultimate boundary. Here, the curvature of space-time is so severe that the escape velocity exceeds the speed of light. Nothing, not even light itself, can escape its grasp once it crosses this line. For our distant observer, something truly strange would happen as the spaceship approaches the event horizon. Time on the ship would appear to slow down until it seemed to stop completely. The ship would appear to freeze at the edge of the black hole, fading from view over an infinite amount of time. The observer would never see it cross the boundary. But what about the astronauts' own experience? For them, time would continue to flow normally. They wouldn't feel time stopping. They would simply cross the event horizon and continue their journey inwards, unaware of the frozen image they have left behind for the rest of the universe. Inside the event horizon, space-time is so warped that all possible paths lead only one way, towards the central point, the singularity. The astronauts' time and space are now completely dominated by the black hole's gravity. A black hole, then, represents the ultimate victory of gravity over time, a place where time, as we know it, is stretched to its absolute limit. Time dilation and warped spacetime might seem exotic, but you use a device every day that relies on Einstein's theories of relativity to function correctly, GPS. Every time you use your phone or car's navigation, you benefit from Einstein's insights. GPS uses satellites with atomic clocks. Your phone receives signals, calculating distance by measuring signal time. Signals from 4 satellites triangulate your location. Relativity is key. Satellites' motion affects time. General relativity also matters. Satellites orbit in weaker gravity, so time runs faster. These effects don't perfectly cancel. When we combine these two relativistic effects, we find that they don't cancel each other out. The effect from special relativity, due to the satellite's high speed, causes their clocks to slow down by 7 microseconds per day. The effect from general relativity, due to their higher altitude and weaker gravity, causes their clocks to speed up by 45 microseconds per day. When you put them together, the net result is that the clocks on the GPS satellites run faster than clocks on Earth by about 38 microseconds every single day. That's 38 millionths of a second. It might still sound like an insignificant amount of time. However, for the GPS system, precision is everything. The system works by measuring the travel time of light signals. Light travels at about 30 centimeters in 1 nanosecond, which is a billionth of a second. If the clocks in the sky were off by 38 microseconds, that's 38,000 nanoseconds. This timing error would translate into a positioning error that grows at a staggering rate. After just 1 day, the entire GPS system would be inaccurate by about 11.4 kilometers. Your phone might tell you that you're in the middle of a park when you're actually on a motorway miles away. The system would be completely unreliable. To prevent this, the engineers who designed the GPS system had to build Einstein's theories directly into the calculations. The atomic clocks on the satellites are deliberately engineered to run slightly slower while they are on the ground. They are set to a different frequency before they are even launched into space. Once they reach their orbit, The combined effects of special and general relativity cause them to speed up to the correct rate, perfectly synchronizing them with the clocks on Earth. Furthermore, the software in your GPS receiver constantly makes tiny relativistic corrections to ensure the timing is perfect. This is a stunning, everyday proof of Einstein's theories. Relativity isn't just an abstract theory for physicists to ponder. It's a practical tool for modern engineering. The fact that your GPS works so flawlessly is a daily testament to the reality of time dilation and warped space-time. Without accounting for the fact that time flows at different rates in orbit and on the ground, one of the most transformative technologies of our time would fail. It's a beautiful example of how a deep understanding of the universe's fundamental laws has a direct and tangible impact on our lives. Relativity's influence extends beyond GPS. Particle accelerators like the Large Hadron Collider rely on relativity. Time dilation affects particles like muons, extending their lifespan, allowing study. Even old CRT televisions accounted for relativity, with electron beams reaching significant fractions of light speed. From navigation to fundamental research, Einstein's legacy surrounds us. Once science fiction, these ideas are now embedded in our technology. A reminder that curiosity-driven research leads to unexpected applications. We have journeyed far in our exploration of time. We began with a simple question: can time slow down? The answer is yes. Time's flexibility is fundamental. We followed Einstein, whose theories shattered our understanding of the world and replaced it with a vision of reality that is far stranger and more beautiful. This forces us to abandon the idea of a universal now. There is no single clock ticking for everyone. Our sense of a shared present is an illusion. This shift in perspective teaches us humility. Science pushes us beyond limitations, offering a glimpse of a deeper reality and the weirdness of the cosmos. Reflecting on these ideas fundamentally alters our relationship with time itself. We started with the image of time as a steady, unyielding river, but relativity has shown us that this river is far more dynamic, with currents shaped by motion and gravity. My river of time can flow at a different rate to yours. This can be both unsettling and liberating. Einstein's universe is a place of shifting perspectives, demanding a more flexible way of thinking. There is a certain beauty in this malleable reality. The fact that an astronaut can journey to the stars and return younger than their twin is a window into the incredible physics that governs our cosmos. Our relationship with time might one day become something we can actively navigate. We are not just passengers, but captains of our own vessels, each charting a unique course through space-time. Our reality is our own, a unique path carved through the cosmos. While Einstein's theories have been tested and confirmed for over a century, they have also opened up new mysteries and pushed the boundaries of our knowledge. His work provides an incredible description of how the universe works on a large scale, the scale of planets, stars, and galaxies. However, it is not the final word. One of the biggest challenges in physics today is reconciling Einstein's theory of general relativity with our other great theory of the 20th century, quantum mechanics. Quantum mechanics describes the universe on the smallest possible scales, the world of atoms and subatomic particles, and it operates by a completely different set of rules. General relativity paints a picture of a smooth, curved space-time. Quantum mechanics, on the other hand, describes a world that is fuzzy, probabilistic, and chaotic at its most fundamental level. The two theories are spectacularly successful in their own domains, but they seem to be fundamentally incompatible. They speak different mathematical languages and offer contradictory descriptions of reality. For instance, what happens at the very center of a black hole, the singularity? General relativity says it is a point of infinite density where its laws break down. Quantum mechanics suggests that such infinities shouldn't exist. To understand these extreme environments, we need a new theory. Physicists around the world are working to bridge this gap, searching for a theory of everything or a theory of quantum gravity. This hypothetical theory would unite relativity and quantum mechanics into a single, elegant framework, capable of describing all physical phenomena from the Big Bang to the inner workings of a black hole. Theories like string theory and loop quantum gravity are leading contenders, but they remain unproven and are incredibly difficult to test. These theories suggest that at the tiniest scales, space-time itself might be made of discrete quantum units, like pixels on a screen, fundamentally changing our view of its smooth, continuous fabric. These unanswered questions are what drive science forward. Einstein stood on the shoulders of giants like Newton, and future generations will stand on his. What lies beyond relativity? Will we ever find a theory of quantum gravity? What is the true nature of time at the quantum level? Does time even exist at the most fundamental scale, or does it emerge from some deeper, timeless reality? These are the questions that will inspire the next generation of scientists, the next Einsteins, to continue our collective journey of discovery, pushing ever deeper into the profound and beautiful mysteries of the cosmos. Our journey through the ideas of relativity has shown us that the universe is a far more wondrous and surprising place than it appears. We have seen that time is not a rigid metronome, but a flexible dimension, interwoven with space to form the very fabric of reality. We have learned that our motion and the gravity we feel can stretch and slow our personal experience of time. What began as a simple story about two twins has led us to the edge of black holes, the heart of particle accelerators, and the intricate technology that powers our modern world. It is a story of how pure curiosity can change everything. The implications of these ideas extend beyond the realm of science. They touch upon the most fundamental aspects of our existence. If time is relative, it encourages us to consider that our perception of reality is just one of many. It asks us to be more open-minded, to recognize the limitations of our own perspective. The universe, in its vastness and complexity, does not always align with our human-scale intuition. Embracing this fact is a crucial step in our intellectual and philosophical development, allowing us to appreciate the cosmos on its own terms, not just ours. The future of discovery is wide open. We are living in a golden age of astronomy and physics. New telescopes are peering deeper into space than ever before, and new experiments are probing the nature of reality with unprecedented precision. We may one day be able to observe gravitational waves from the very beginning of time, or find direct evidence for a theory of quantum gravity. The questions that Einstein's work raised are still guiding our exploration of the universe, leading us towards an even deeper understanding of space, time, and our place within them. The journey is far from over. So, the next time you look up at the night sky or check your location on a map, remember the hidden reality that Einstein unveiled. Remember that you are a traveler through a four-dimensional space-time on your own unique path. Your personal river of time flows at a rate determined by your every movement. The steady ticking of your watch is a local, personal truth, not a universal one. The universe is a dynamic, interconnected, and relativistic place, and our quest to understand it is one of the most noble and exciting adventures we can undertake as human beings. Our journey through space-time has only just begun.